Hello. In this video, we are going to cover conditional probability. So what is conditional probability? It's a probability that is calculated on the condition that something happens. So what I'm going to do is I'm going to go through and break this up into two different types of conditional probability. So we're going to talk about, so first of all, you can see the condition is in the name, thus conditional probability. So a condition needs to be met. And we're going to break it up into a criteria or a characteristic and an action. All right, so there's kind of going to be two different types of conditional probability. So let me just give you a brief examples of those. So when it comes to a criteria or a characteristic type of conditional probability, so we're talking about something like the probability that you make a certain income based upon having a college education. So it'd be something like a probability that a person makes, let's say $100,000, we'll just pick some level, given that they have a college education. So what we've got there is we've got a probability that we're looking to calculate, which is that a person makes 100,000, and then we have a condition, and that condition is that they have to have a college education. All right, so we'll go through how to calculate that, but I'm just giving you an example of what conditional probability looks like. So this is a criteria, all right, so or a characteristic that a person has. So the person has a college education is the condition. All right, the other type is based around an action. So that might be something like the probability that an ace is drawn from a deck of cards. Given that an ace has already been drawn. From the deck. All right, and so it's similar. All right, so what we've got is we're trying to find the probability of something happening, given that something else has already occurred. All right, so in this case, given that there's a condition is already in place. Okay, and so so we're going to go through and we're going to look at criteria conditional probability, and we're going to look at action-based conditional probability. The textbook that we're using combines these basically into a single type. However, I'm going to split them apart because I think it actually makes it easier to understand them if you go through and break them apart. Otherwise, there's examples of things that they give that are based upon actions that don't really smoothly apply to criteria. It does end up working. All right, so the definitions and things that you end up using for these it does turn out that they're interchangeable, but I think it's kind of difficult to see that, and so I think it's easier to go through and kind of break them apart into the two separate cases, and then and then show show that everything works for both. Okay, so let's move on to actually going through and calculating a conditional probability. Let's go through and calculate a conditional probability. And the one that we're going to do, we're going to end up using a table from the last section. What we want to do is we want to go through and find the probability that a college-educated person is married. We're going to use the table from the last section, which I'll bring up in a second. Okay. Before we do that, though, so you'll notice the language that I used here is a little bit different than the language I used on the previous page. So I used this given that on the previous page, right? So you see given that, given that. So you can see, you'll sometimes see conditional probability written this way, where the given that the condition is the second thing. It always comes after the given that. So they'll say, given that some condition is met, go through and find the probability. However, sometimes these conditional probability problems are written so that given that is not explicitly in there. And then you just need to be able to read, through reading comprehension, be able to identify what's the condition and what's the thing that you're finding. So this is saying find the probability that someone who's college educated is married. All right, so the college educated is the condition here. All right, so they're saying someone who's college educated is married. The thing you find the probability is you find the probability that the person is married given that they're college educated. So just reading comprehension, you need to be able to identify what the condition is. And the condition is it should be obvious if you kind of go through and read it. All right, sorry, that's bugging me how ugly that line was. All right, so let's actually go through and do this. All right, so here's the table from the previous section. It has the information that we need to be able to go through and do that. And we want to find the probability a college-educated person is married. How do you do that? All right, so what it's saying is that you have to have the person be college educated. That's a requirement, it's a condition. And so the way that you can go through and represent that in terms of calculating the probability is you can go through and you can just take that part of the table. That's like we're going to restrict the table to just the part where we have college educated people. If you're not college educated, then the probability here, you don't matter. All right, so you're not counted in terms of going through and calculating the probability. The only thing we care about are just college educated people, and so we can go through and ignore everyone else. All right, and if you do that, then you can go through and the probability is actually relatively easy to calculate at that point. It's just a matter of finding, all right, so we want married people. So what's the probability that someone's married? So you want the number of people that are married over the total number of people. How many total people who are college educated? 143. Okay, and so that's the way that you can go through and do these conditional probability problems. You take the condition and you use it to restrict like you want just that part of a table or that part of a problem that you're working on, and you just want to go through and calculate the probability within that subset, within that subsection of the data. Okay. So a reasonable question that comes up is, how does this differ from going through and finding the probability that someone is college educated and they're married? So we did that in the last section. So let's just look at that. So if we said find the probability that a person is college educated and married. right? So if you're doing that, then again, so now you have to ignore that box that we just put in there. Now we're talking about the entire table. We want to find the people who are both college educated and married. All right, so college educated and married, that's right here, 98. And now there's no restriction here on other people. So the less than high school people, the high school people, they're all in there. Single people, divorced people, they're all in there. And so this goes over 665. Okay, so the difference between these, the difference between these is in terms of, is the condition goes through and restricts the table for just a subset of it, just part of it. And so when that happens, your event space, like to use the terms that I used in the last video, your event space is going to be 98. And then your sample space, your total sample is just going to be the college educated people. So that's 143. Meanwhile, if you want to find college educated and married, then your event space is still that 98, but the sample space is now 665. And so that's the difference between going through and doing a conditional probability and doing an and probability, is that your denominator is going to end up being different. Otherwise, they're pretty similar. All right, so let's go back to our whiteboard and introduce some notation. We're going to end up coming back to that, coming back to our table in a minute. All right, so notation. How do we represent conditional probability? So the way that we would represent this problem that we just did is we'd say, find the probability a person is married and we're going to put a line, and I'll talk about that in a second, and then the person is college educated. So we put the condition second, and we put the thing that we're trying to find the probability of first. And this bar is pronounced given that. And if you pop it in, then it turns exactly into the language that I initially used to describe conditional probability. Person is married, given that person is college educated, right? Person makes 100K, given that they have a college education. All right, so this would be the thing that we're finding the probability of. This is the condition. All right, so that's how it works. The thing we're finding the probability of goes first, and then the condition goes second. Notationally, in terms of a formula, there's a formula that we can use for this. So I'm going to go ahead and replace person is married with A. I'm going to replace the person is college educated with B. So we have just symbols here, and that equals, you can rewrite this. This is the probability of A and B divided by the probability of B. All right, so this is essentially a formula that we can use to go through and calculate conditional probability. We did something kind of like this on the problem, but also not really. So let me show you that actually using the formula, and it will be, it's a little bit different. And in my opinion, it's maybe a little bit overkill, but it does work. All right, so the formula here would say you'd have probability. So we're trying to find the probability someone is married, so we'll call that A, college educated. B, so we've got the probability of A given B, and that's supposed to be equal the probability of A and B over the probability of B. What is the probability of A and B? Well, we did it right here, 98 over 665. What's the probability of B alone? Okay, so we did not calculate that, but we can. What's the probability of someone being college educated? So that now we're not doing any restrictions here. Now we're just using the whole table. Someone who's college educated, how many college educated people are there? There are 143, so you get 143 over, I gotta move that up a little. You get 143 over 665. And then if you simplify this, you get 98 over 143. Now that's the same answer, but you could see it was a little bit more involved. I like the way that I did it the first time. That's the way that I do conditional probabilities, to go through and, mentally, or you could actually, put a box around the, the part of the table that's, that's the condition, and you just kind of go through and restrict the sample space. I think that method, I think that works fine. I don't think it's overly confusing, but if you want to, you could do it this way, where you find the probability. Basically, what this is enabling us to do is it's to find the probability using the formulas from the last section. Okay, so that's the idea here, is we can go through and we can rely upon the methods that we used in the last section, and just use those to go through and find the probabilities in this section, rather than to invent a new method, this idea of restricting the sample space. But I like restricting the sample space better. I think it's simpler. Okay, let's jump back to our whiteboard here. So a couple notes. This formula can be rearranged by moving the probability of B over to the left-hand side. So it can be rewritten as probability of A and B equals probability of B times the probability of A given B. All right, so this formula is going to, it's a different formula. We're going to end up using this in a second. So this, we're going to come back to. I'm going to come back to this. The way that you could read this is that the probability of A and B equals the probability of B times the probability of A given that B has happened. What this is going to end up turning into is it's going to end up turning into a formula for us to calculate probabilities for multiple events happening, like actions. So we haven't talked about actions at all yet, other than the kind of the initial definition I gave. But like I said, we're going to come back to it, and then it will be clearer. So also, these are places where students sometimes get confused. The probability of A given B is not equal to the probability of B given A. It's important to know. Maybe not obvious, just because we're kind of used to from math, that frequently there's there's properties that say that these kinds of things are true. This is not one of those cases. If you actually think about what these are saying, like if you pick an example, let's ignore the college educated married thing, because it's maybe a little bit more difficult to understand the relationship there. But if you used something like college educated and $100,000, over $100,000, then what you've got on one side is you've got the probability that you'd make over $100,000 given that you went to college. And on the other side, you have the probability that you went to college, given that you make $100,000, and those are just not interchangeable. Those two conditions are going to be different. If you're finding the probability that you make over 100,000, given that you went to college, versus the probability that you went to college, given that you make over $100,000, those are just language-wise, in terms of just thinking about what we're saying there, those are not the same. And you can even prove that these are not equal by actually using this formula that we derived. This side would be the probability of A and B over the probability of B. And this side is the probability of A and, actually it's B and A, but who's counting? So A and B over the probability of A. So these are not the same, okay? Unless A and B are the same. If A and B are the same, then these would be equal, but in general, they're not going to be. The probability of A and the probability of B are not going to be the same. So in general, these are not equal. And then the other one, let's see, I got to check my notes here. So probability of A given B and then equals 1 over the probability of B given A. So sometimes people want to do this. This is not true. You can't go through and treat the conditional probability like it's a negative exponent. So you can't do this. So you can't swap the probability thing and the condition thing, and without changing the what you're finding, and you can't go through and swap these and take the reciprocal. That does not work either. All right, next, let's talk about independent versus dependent. Oh, wait, hold on. Actually, I think there was one more probability we were supposed to do, because before I introduced this, I was supposed to do another probability. Oh, yes, we were supposed to do one more. My apologies. We'll have to come back to this independence, because otherwise my intro is not going to make sense, because we didn't do the second probability. All right. So let's do one more example. Okay, I don't have a quick way to erase things, so just 1 second. You put the video on, fast forward while I go through here and erase some stuff. Actually, hold on, I'm gonna use a trick. It's a trick that you can do. This is all in MS Paint. You can grab some white space, slide it over, grab some more, slide it over. All right, so the second example we were going to do, I forgot. So we want to find the probability a less than high school educated person is married. So just so you have a second example. All right, so we want to find probability married, given that less than high school education. All right, and I'm going to go through it. I'm going to do it the same way that I did it the first time, because I think that's easier than using that complicated formula. So what we're going to do is we're going to restrict the part of the table that has less than high school. So the condition here, we want to find the probability that someone's married, given that they've got less than high school as the condition. So the way that these probability problems work, you want to eliminate everything that does not meet the condition. So the only things that meet the condition are going to be the things that are in this box. So I'm going to box in just the part of the table that meets the condition. And then what we can do is we can, from there, just pretend the rest of it doesn't happen. Like you can just scribble over it. The rest of the table does not exist when it comes to finding the probability. So we want to find the probability that someone's married. All right, so that's going to be, there are 70 people in our event space that would meet that criteria. And then over how many total less than high school people? 125. So that's how you do it. That's how you calculate conditional probability. And because my introduction requires it for the next problem, we want to compare these. Are these the same or are they different? So the way that we can compare them, you could break out a calculator and take your calculator, divide 98 by 143. And when you do it, you're going to get about 68.5 or 0.685, which if we change to a percent is about 68.5%. And then go ahead and take 70 and divide it by 125. And you get 0.56 or 56%. Notice these things are not the same. We got different values. All right, so the probability of being married if you have a college education is different from the probability of being married if you have less than high school. Okay, when that happens, we're going to have a special name for that, and that's the next section. All right, independent versus dependent probabilities. Oops, nice spelling job there. And there's another term for dependent called associated. All right. So when we go through and we calculate a probability and we get different values with different conditions, then we say that those probabilities are dependent. We say that there's a dependent relationship between the two criteria. Oops. So what does that mean? What do we mean by that? So if we go through and calculate the probability that someone is married given they've got a college education, and we calculate someone is married given they've got less than high school, and we get a different value, what that means is your education level is related. There's a relationship, there's a connection between your education level and your chance of being married. All right, and so that's what we're saying is associated, those two things, education level and your chance of being married. All right, so this is another way of saying there is a connection between the criteria whose probability we found, whose probability was different. So in this case, education level and marriage. So that may be a surprising result, that your education affects your chance of being married. But there are more obvious examples of dependent or associated criteria. And we started off with one at the very beginning, and that would be your income level and your education level. So typically people would say that there's a connection between those two. You see lots of tables, when you're in high school, which show the amount that you'd make with a high school education, the amount that you'd make with some college, the amount that you make with a bachelor's degree, the amount that you make with a master's, and then with a PhD, right? Have you ever seen one of those tables? Those tables are saying there is a connection between your education level and your income level. And so in that case, we would say that those things are dependent or associated. All right, so that's the terminology we use when we have that situation. Now, there is also the opposite situation. So you could go through and find the probability of things and end up getting the same result. When that happens, we would say that the two things are independent. So I haven't given an example, that works that way. But actually, let me finish this. Let me kind of copying what I did above here. What that's saying is that there is no connection between the criteria whose probabilities that ended up being the same. So what will be an example of that? Let's stick with our education level thing. So when we said that the probability that you were married and given your education level, we got different outcomes, which told us that those things were connected. What would be an example of something where you'd expect the probability would be the same, okay, regardless of your education level? And think about it for a second. What would be something that would not be related to education, where education would not end up providing us any knowledge of what we would expect? All right, so that's the main thing that we're looking for here when we're talking about things being dependent. The education level tells you something about the person. It gives you an insight into their background, their preparation, which is what tells you that that person is going to have a higher income. What would be something that where you'd get nothing from knowing someone's education level? The examples I could think of were things like genetic markers like hair color or eye color, or maybe even handedness, left-handedness or right-handedness. We would expect those things to be independent of education level. We would not expect that people who have some college background, that a higher percentage of them have blue eyes. That doesn't make sense. And so that would be an example, would be of things that would be independent, would be like eye color and education level. So what we would expect to compare with the experiment we did earlier is that if you went through and found the probability that someone had blue eyes, given that they were college educated, you'd get some number. And then you went through and found the probability that someone had blue eyes, given that they had less than high school, you would expect those probabilities to be the same. By getting the same probability with two different conditions, that tells you that the conditions that you didn't get any information out of the conditions. The conditions were useless when it came to going through and getting finding some advanced knowledge that you could use to determine a person's eye color. The examples that you'd need for eye color to be dependent would be probably to look at like a parent's eye color, right? So if you had the probability of finding someone had blue eyes, given that one of their parents had blue eyes, then suddenly you would expect that to be dependent. You would expect that there to be a connection between those two criteria, but there's clearly no connection between eye color and education level. Okay, so up to this point, we've focused heavily on criteria. Let's talk about actions. First, what do we mean by actions? What are examples of actions? So could be, pulling a card from a deck of cards. Rolling a dice. Or rolling a die, I guess. Dice is two, dice is plural. Could be flipping a coin. So we can go through and we can calculate probabilities with these things, and we can calculate conditional probabilities. So let's look at some conditional probabilities. So we already talked about one, the probability of drawing an ace given that you've already drawn an ace. And we can go through and we can calculate these without, you don't use a table for these. Instead, what you do is you think about the effects on the, if you want to call it the event space, which term I used in the last section, and the sample space. So how many different ways are there of satisfying the event that you're looking at calculating the probability of versus how many total things are in the sample space. So in this particular case, you need to have a basic understanding of cards to go through and do this. So let's just real quick review. There's 52 cards in a deck. There are 4 suits. There are 13 cards from each suit, and those cards are ace through king. We will use ace as the low end. Sometimes it's used as the high end, but you could think of ace as 1, and then you have 2, 3, 4 up through 10, and then jack, queen, king. So there's 13 total of each suit, and you could do 4 times 13 to get 52. So the way that you want to go through and calculate a conditional probability with a deck of cards is we want to think about the state of affairs. You want to think about the situation that you start with and then go through and modify that situation based upon the actions that have taken place, the actions that you're looking and finding the probability of, the conditional probability of. So in this particular case, we're talking about aces. So we start off with 4 aces. There's 1 ace from each suit. And then there's 52 total cards. So this is kind of the starting situation, if you were to think of this like an experiment. And then let's say that we went through and our condition that the probability is based upon, the given that here is that we've drawn an ace. So we've already drawn an ace. What happens when we draw an ace? How many aces are going to be left? So if we pull an ace out and there's 4 to start with, and there's only going to be 3 aces left. Okay, and then if there are 52 cards to start with and we pull 1 out, there's going to be 51 total cards left. All right, so this is what happens if we go through and draw an ace. And then from there, if we want to go through and calculate what's the probability that we draw another ace, given that we've already drawn one, we start off with this situation and we just look and just count event space versus sample space. All right, so we're drawing an ace. So how many ways are there to draw an ace that are left in the deck? There are 3 aces left. So there are 3 ways to get an ace. And then what's the size of the sample space? So there's 51 total cards. So you've got a 3 out of 51 chance of grabbing another ace after we've drawn 1 ace. Okay, and so that's an example of a conditional probability with actions. And so, we could go through and we could still have dependence, just like we did with criteria. We could still have independence. So let's go through and just do another quick example here, just so that we can so that we can represent some equivalent to our situation with the married versus education level. So let's say we wanted to go through and calculate the probability of drawing an ace, given that we've drawn a non-ace, something that's not an ace. Okay, so we want to go through, and so that could be a 2 or a 3 or a king or a jack, anything that's not an ace. All right, so if we start off, we've got 4 aces out of 52 cards. We draw a non-ace. How many aces are going to be left if we've drawn something that's not an ace? All right, there's still going to be 4, right? If we started with 4 and we draw something that's not an ace, we're still going to have 4. And then if we draw a card, we started with 52. How many are going to be left after we draw a card? Even if it's a non-ace, we're going to have 51 left, right? And so if we want to go through and find the probability of drawing an ace, assuming we've drawn a non-ace, we have 4 aces left to satisfy our event space. over the 51 total possibilities, the 51 size of the sample space. And so we get 4 out of 51. And so we could see here that you get a different probability depending upon whether you've drawn an ace or whether you've drawn a non-ace. Okay, and so with different probabilities, that's when we have our dependence versus our independence relationship, just like with the criteria. So let's take a look at that. All right, so technically the definition is the same. So technically, we have a dependence relationship between actions when you end up getting different probabilities. I'm sorry, when the conditional probabilities are different, actually, to be specific there, when the conditional probabilities are different. In practice, though, that's not the way that I think about it. When I don't actually go through and calculate the probabilities. In practice, the way that I think about it is, is the situation that you're looking at, let's call it an experiment. So the action, let's say the action that we're doing, is an experiment, just so that we have a term that we can wrap our heads around. So is the experiment changed by the first action taking place before the second action? So does the first action change the experiment, change the conditions, change the situation before the second? That's what I think. So in practice, dependence is based upon whether the first action changes the experiment, situation, whatever word you want to use to, in this case, the situation we're looking at is pulling cards from the deck. Does it change the deck of cards? Whether the first action changes the experiment / situation before the second action. And the example that we just looked at is just a classic one, and that is when you pull cards from a deck, the card pulls are going to be dependent upon, the probability of getting a card is going to be dependent upon what the first card you pulled is. So the probability of getting an ace is going to be dependent upon whether you've already drawn an ace or whether you drew a non-ace. All right, so pulling cards from a deck, you're going to have, those are going to be dependent. So we're going to get dependent actions. If you pull marbles from a bowl of marbles, then that's going to change the probability, right? So just to be more explicit, so let's say you have a bowl that has 20 marbles in it, and you've got 7 red, 7 green, and then 6 white. If you go and you pull a marble from the bowl, and then ask after you've pulled that marble what the probability of the next marble is going to be, whether it's going to be red or green or white, the probability is going to depend upon what the first marble that you pulled was. And so the way to think about dependence when it comes to actions is, does the experiment, does the thing that you're doing, does it change when you go through and do the first action before the second? If so, then you have a dependence or associated actions. All right. And I think this will make even more sense when you actually can compare it with independence. So let's talk about just independence real quick. So again, technically, when it comes to independence, if you end up getting the same probability, then two actions are going to be independent. So if you get the same conditional probability, then the actions are independent. However, in practice, what we think about, or what I think about when it comes to determining whether actions are independent is, does the action change the experiment that you're doing? Does the action if not, then they're independent. So what are examples of things, of actions that you can do? And I listed some on the previous page. What are examples of actions that you can do where the situation is not changed by performing the first action? And examples, I think we can fit this on here. Rolling a die. If you go through and roll a dice and get a 6, and then someone says, what's the probability that you're going to get a 6 on the second die roll? The fact that you got a 6 on the first die roll does not change the probability of getting a 6 on the second die roll. They are completely unrelated. Okay, the situation is not changed. The die is not changed by going through and rolling a 6 the first time. And so rolling dice are independent events, independent actions. Flipping a coin. If you flip a coin and get heads, that does not affect whether the next coin flip is going to give you heads or not. Again, getting heads on a coin does not somehow magically change the coin and make it so that it has a different probability for additional coin flips. Okay, and so flipping a coin are independent events because the first flip does not in any way change the experiment of flipping the coin or change the situation. The situation is exactly the same. You flip a coin, you catch it, and then you go to flip again, and it's literally the exact same thing that you're doing the second time. And then there's ways to go through and take these previous two examples and also make them independent. If you pull cards from a deck and then you replace them back in the deck, then it takes a dependent event and makes it into an independent event. And so what you'll see is that the phrase with replacement, when you see with replacement, what that's doing is that's making it so that the events are independent, so the actions are independent. All right, so I'm just going to put with replacement because there's not really enough room, but that goes for cards, marbles, any type of situation where you end up pulling something, as long as it's with replacement, that those events are going to be independent. Okay, by going through and replacing it, you've made it so that the situation or the experiment or whatever you want to call the thing that you're doing, that it's not changed, it's the exact same thing, right? So you go through, you pull an ace from the deck, and then you put the ace right back in. The deck is exactly the same as it was, was originally. You haven't changed it by when you go through and when you go to pull another card, you haven't changed it, and so that's made it so that the events are independent. Okay, so one thing before we move on from this dependent stuff, because this is going to be important. And so this goes for criteria, it goes for actions. And so it's another way of looking at independence. So we have the specific phrase. So what it means to be independent is it means the knowledge of event B, and by event we could mean criteria or action, event B happening. So knowledge of event B happening does not change the probability. So this applies both to criteria or actions, but I think it fits better with the action definition that we just looked at. So now events are going to be independent if knowing that an event has happened does not change the probability of the next event happening. So the example would be if you go through and you roll a dice, then whatever outcome you get, it does not change the probability of the next outcome from happening. So if you want to know the probability of rolling a 6, given that you've already rolled a 6, the given that you've rolled a 6 makes no difference on the probability that you're going to get a 6. Okay, the same thing for coin flips. The knowledge that you've flipped ahead does not change the probability that the next coin flip is going to be ahead. And so the idea of independence is it's a way of going through and measuring whether the two things are related, are connected in some way. So with actions, if the events are completely unrelated, if they're disconnected, then that's going to be when you get independence. If the first action does not end up affecting the probability of the second action, if knowledge of the first action does not tell you anything about the second action, then that's what it means to be independent. All right. And that also applies for criteria as well. It's just a little bit harder to wrap your head around that using that definition for criteria, but it means the same thing. Okay. So what this is a translation of is that if you have conditional probability, like the probability of A given B, all right, so this is the probability of event A happening, given that event B has happened. If event B doesn't give you any information, it doesn't tell you anything about the probability of event A, if they're disconnected, there's no relationship between them, there's no connection, then so that B is not at all helpful, like rolling a die and getting a 6, does that tell you about the probability of getting another 6? If the answer is no, then what that means is that the probability of A given B is equal to the probability of A. All right, so B was worthless in terms of figuring out what the probability of an event was. And so if you think about that, this is the probability of rolling a 6, given that you've already rolled a 6, is the same thing as the probability of just rolling a 6. The knowledge of the first 6, didn't give you anything. That's a way to go through and take this independence definition and turn it into like a formula and turn it into a notation. And so you can go through and use this formula to measure whether events are independent, right? So we know how to go through and do conditional probabilities. We know how to go through and do regular probabilities. So what we can do is we can go through and calculate, we can calculate the left-hand side, we can calculate the right-hand side. And if we end up getting the same answer, then that will give us a way to measure whether there's independence or not. And if we get different answers, then that will tell us that there's dependence. So this formula gives us a handy way to go through and determine whether there's dependence or independence. So let's go through and try using our formula. Now, this is going to be confusing. I apologize, but this is the example they gave in the text, and I've been sticking with doing the examples from the text. All right, so this is going to be a criteria problem, but it's with cards. So we're not talking about actions. We're talking about criteria. All right. Let's say given you have a deck of cards. Are the criteria a card is a diamond and a card is red? dependent or independent. Now notice there's no mention of drawing cards here. So we're not drawing cards. This is an actual criteria problem. This is like the marriage, college education thing. It's just, we're just using cards for it, which again, I apologize. That makes it a little bit confusing. But so what we're looking to do is our check is to go through and compare the probability of A given B with the probability of A. All right, and so what we can do here is we can go through and find what's the probability that a diamond, we've got the diamond is red. Sorry, the probability that given a red card, it is a diamond, versus the probability that a card is a diamond. All right, so what is the probability that we've got a diamond given that we've got a red card versus the probability of just having a diamond? Okay, so again, if we start off with our 52 cards, all right, so how many red cards are there? So I didn't talk about that in the previous example, but when there's 4 suits, 2 of the suits are red. Okay, so 2 suits are red. And one of those suits are diamonds. So if you're looking at what's the probability that we've got a diamond, given that we have a red card, the event space, how many diamonds are there? There are 13 diamonds. How many red cards are there? Well, there are 2 suits of red, so there's 26 red cards. And so that's the probability that we've got a diamond, given that we've got a red card, versus the probability that we've got a diamond. So what's the probability that we've got a diamond? Well, there's 13 total diamonds out of 52 cards. All right, and so this reduces to 1/2, this reduces to 1/4, and so we got a different, so these were not equal. If these were not equal, what does that tell you? It tells you that these 2 things were dependent, these 2 criteria. So the criteria, a card is a diamond and a card is red, are dependent. So just like the example with the criteria of college education versus married, okay, and the kind of the neat thing about being able to use this test and do this problem is that you don't need to go through and think about whether there is a connection between these things. The formula, assuming you go through and calculate the probability correctly, the formula will just do it for you. But it does turn out that there is a connection between being a diamond and being red, which kind of makes sense because diamonds are red. All right, so that's the idea there, is that if you were trying to use the logic, like to think about it in terms of like the example with college education versus income, if you were to try and use your intuition to answer this, the way to think about it is being a diamond and being red related? Well, diamonds are red, so the answer is yes. Let's do another example like that. And again, it's another card example. So sorry. It would be better if these were not card examples, but that's what we've got. Are the criteria a card is a diamond and a card is an ace? Dependent or independent? All right, so intuition wise, is there a connection between being a diamond and being an ace? No, right? So aces are sometimes diamonds and aces are also not diamonds. So being an ace does not make you in any way, shape, or form a diamond. So intuition-wise, you would think that these criteria are independent. And so to check that, we can go through and calculate the probability that something is an ace, given that it's a diamond, versus the probability that something is an ace. So this is probability of A given B equals probability of A. All right, so again, the way to handle this is just in terms of thinking in terms of event spaces and sample spaces. So how many aces are there? There's that are diamonds. So we've got one ace out of 13 diamonds. So I don't know if I need to review this, but the way to think about this is you first want to use the condition to limit the sample space. And so if we start off with 52 cards, the given that here is a diamond, so we want to restrict it down to just diamonds. So there's 13 diamonds, and then how many of those are aces? One of them. And so that's the way to do this left-hand side here, is there's one ace amongst 13 diamonds. Meanwhile, what's the probability of drawing an ace from the entire deck? There are 4 aces in the entire deck out of 52 total possible cards. So without the given that diamond, we want to think about the whole deck. So on this side, we're thinking about aces just amongst diamonds. On this side, there's no given that, so we're thinking about all the cards. And if you go through and reduce these, you get 1/13 equals 1/13. And so check, these are independent, which is what our intuition told us. Okay, so let's go ahead and look at doing probabilities for sequences of events. And I believe these are all actions. So let's not use events, because events is kind of, has that connotation that we're talking about criteria as well. I think it's simpler if we just think of these in terms of actions. I think these are all action related. But the idea is that you could try and take sequences and use it for criteria, I think, as well. But it's more difficult to think about it that way. It's just a little easier contextually to specifically think about this in terms of actions. So what we're going to look at is we're going to look at 2 possibilities. We're going to look at dependent and independent. So we're looking at sequences of actions. So if we have independent, we're going to do independent first. Then the thing that's going to be critical is we're going to end up using that formula earlier. So this is the probability of action A and action B. So now we're thinking in terms of actions. So this is action A, this is action B, and they both happen because we're talking about a sequence of actions. So we're talking about 2 actions that both take place. All right, so probability of action A and action B, and then using that formula from earlier, like all the way back here. Oh, whoops, I forgot. I had to restart the video at one point. So the formula for probability of A and B equaled the probability of B times the probability of A given B, right? So you should be able to go back into your recording of this video and see that, but I can't go back in mine because I had to restart. And so the probability of A and B equals the probability of B times the probability of A given B. However, with independent events, we know the probability of A given B equals the probability of A. So you can rewrite this as the probability of B times the probability of A. All right, and this is because of independence. Independence tells us the probability of A given B equals the probability of A. That was what we were just, that formula is right here, a couple pages back. So that one we can see. So that's for independence. So we're talking about independence first. And for independence, the probability of for action A and action B, two different actions that happen in sequence. We'll do examples in a second that will make it clear that these happen in sequence. The two events happen, and the probability of those two events happening, we used our formula from earlier, and then we simplified that formula by the fact that the events are independent into just being able, all you got to do is just do the product of the two events separately. So that's the wonder of independence. When you have independence, it's very simple to go through and calculate the probability of sequences. You just need to go through and multiply by the probability of the events happening individually. All right, so let's look at an example of that. All right, so suppose the probability of having a boy is 51%. Find the probability of having two boys. Two boys. All right, and then find the probability of having a boy then a girl. Okay, so how do these work? So they're really, I don't like to use the word easy because, but they're not very difficult. All right, so the probability of having a boy and a boy. So the idea is that someone has, these are sequences of events, right? You have a boy, then you have another boy. All right, so that's specifically what we're talking about here. So, of course, so first of all, you gotta think about, are these dependent or independent? So if you get pregnant and you have a boy and then you get pregnant again, is the fact that you had a boy the first time, does it affect the probability that you're going to have another boy? The answer is no, absolutely not. They're independent. They're just like coin flips. So it's just like if you flipped a coin, you got heads, and then you went through and you flipped it again, the probability that you get heads is not affected at all by the fact that you got heads the first time. And so because these are independent events, we can go through and write this as the probability that you had a boy times the probability that you had a boy, right? We're using this formula right up here. A and B, action A and B, have a boy and have another boy, probability of B times probability of A. All right, what's the probability of having a boy? It's 51%, so 0.51 times 0.51, and then you'll need to break out a calculator. So I did not do this in advance. So 0.51 times 0.51, we get 0.2601. All right, which is approximately 26%. So your probability of having two boys is approximately 26%. What's your probability of having a boy then a girl? Again, these are independent, so we can do probability of boy times probability of girl. Probability of the boy is 0.51, probability of the girl, 0.49, right? Their complements, 0.51, 0.49, you get 0.2499. So approximately 25%. Okay. Let's look at another example. So let's say we're tossing a coin. Tossing a coin? Flipping a coin, right? Yeah, flipping a coin. I wrote down tossing a coin. Tossing a dice. Tossing a die. So you're flipping a coin 3 times. what is the probability that you get tails 3 times? What about heads, then tails twice? All right. Flipping a coin, they're independent events. So if we want to get tails and tails and tails, that's our sequence. Tails, tails, tails. Since these are independent, we can just multiply them. Probability of tails times probability of tails times probability of tails. And what's the probability of tails? So that's 1/2, 1/2, and 1/2. And we multiply those, you get 1/8. What's the probability of doing heads and then tails twice? That's the probability of heads times the probability of tails times the probability of tails. And that also is 1/2 times 1/2 times 1/2, which is 1/8. Okay. So if that seems a little strange, if you're like, wait, but rolling a head and 2 tails, shouldn't that be different from 3 tails? Well, the issue is the order. All right. So if we said what's the probability of rolling a head and 2 tails out of 3 dice rolls, then the order, if we went through and did each order, we would go through and we would get different probabilities. So the probability of doing heads, then tails is the same as tails, then tails, then tails. But we could also do the probability of tails, then heads, then tails. That would get us another 1/8. The probability of tails, then heads, that would get us another 1/8. And so you could go through and there's 3 different ways you could get a head with 2 tails. And so, yes, the probability of a head with 2 tails with where the order doesn't matter is going to be higher than doing tails 3 times. But when you specify the order, that makes it so that the probabilities are no different. All right, now one more here. So these are examples with complements. All right, so we got some background here. So according to a survey, this actually specifies a Marist survey. Marist must be some type of surveyor. According to a Marist survey, 68% of American adults believe in intelligent life on other planets. Suppose we selected 3 people at random from all American adults. What's the probability that all 3 believe in intelligent life? All right, so technically you should go through and think about whether these are independent or dependent. All right. If you want to be technical, they're probably not independent, because of the issue is if you go through and take somebody out, then that's going to affect the population that's left. However, in this case, the population is so large that I don't think it matters. And so what's the probability that all believe in intelligent life? We're just going to treat these as independent. So you have the probability that, let's see, this is, so the first believes, well, actually, maybe these are independent. What am I saying? It doesn't change the, it doesn't change the rest of the population if you go through. I was thinking that it would be like the deck of cards, but I guess it's not like that. All right, so what's the probability that all three believe? If these are independent, then you can go through and just multiply the probability that they believe separately. So you'll get 0.68 times 0.68 times 0.68. And again, we need a calculator for this. 0.68 times and we get 0.31444. We'll call that roughly 31%. What's the probability that none believe? So we get the probabilities that the first does not believe. And the second does not believe. And the third does not believe. I don't run out of space there. You get the idea. So you go through and so what we need to do is, if someone believes that's 68%, what's the complement of that? 32%. So the chance of not believing is 32%. So we want to do 0.32 times 0.32 times 0.32. And again, you got to break out your calculator. 0.32 times 0.32 times 0.32. You get 0.032768. We'll say that's roughly 3.3%. All right, and then so there's an example with complements. And then what's the probability at least one believes? So this is actually a really important example because this type of probability that at least one thing happens occurs all the time. It's a very regular type of probability to calculate. And so it really should be in your toolkit. And the way to look at it is that at least one believes is the opposite of none believing. Right. So if you think about none believing, so the first does not believe, the second does not believe, the third does not believe. The opposite of that is going to be that one of those or more believes. So this is the complement of none believe. All right. And so just a refresher, the probability for complements of events is 1 minus the probability of the event. And so to go through and find the probability that at least one believes, we can go through and do 1 minus the probability that none believe. In other words, 1 minus 0.032768. And break out your calculator one more time. 1 minus 0.032768. We get 0.9627. Sorry, 967,232, or about 96.7%. All right, so that's sequences of events when they're independent. What about sequences of events when they're dependent? I hope this video is not like 2 hours long. Or associated. All right, so associated is another word for independent or for dependent. So sequences of events with dependence / associated. All right, so when we're doing that, then now if we have the probability of A and B, so probability of event A, sorry, or action, we're doing actions here, I forgot, actions. Think of this in terms of actions. Action A and action B, where there are dependents, then now we have to just stick with the original formula, which is the probability of B times the probability of A given B. All right, so you can't go through and just find the probabilities of these separately. You're going to have to go through, find the probability of the first event, and then multiply it by the probability of the second event, given that the first event happened. Okay, so we've got probability. So that we're actually putting the first event second now here. With the independence, it didn't matter that we reverse the order, but the first event has to be B now, and then the second event is going to be A, given that B happened. All right, and so this is the formula that we're going to use for dependence. All right, so how does that look when we actually do an example? All right, these events are complicated. All right, so suppose we're studying Tour de France. Cyclists. Suppose 2% of them use steroids. Suppose there is a test will be positive 99% of the time when the cyclist has used steroids. So there's a test will be positive for steroids 99% of the time when the person has used steroids. Suppose the test will be positive for steroids 3% of the time when a cyclist has not used steroids. All right, what have we got here? So then it says, what is the probability that a cyclist is steroid free and test positive? So the probability of a randomly drawn, that's important. Probability that a randomly drawn will be steroid-free then test positive. All right. So we want to use our formula, probability of A and B. So we're going to say the probability they test positive and they're steroid free. That equals the probability they're steroid free times the probability they test positive, given that they're steroid free. All right, I almost had enough space there. If I had started writing over a little further over, I would have. All right, anyway, so what's the probability that they're steroid free? All right, so we know that 2% use steroids. So what does that mean? It means that 98% are steroid free. So we've got 0.98 is the first probability. And then what is the probability that they test positive, given that they're steroid free? Suppose the test will be positive 3% of the time when the cyclist does not use steroids. So that's the thing we need. So we've got the probability they're steroid free, the probability the test is positive given that they're steroid free. So that's 0.98 times 0.03. And if you break out your calculator, you can calculate it. It's 0.98 times 0.03. So we get 0.0294. So that's about 2.9%. One of the neat things that you can do with these conditional probabilities, with these sequence of probabilities where they are dependent, is you can go through and you can create probability trees. So let's do it for this problem. So we have a cyclist. So there is, these are a sequence. You can think of these as being a sequence of events. So does the cyclist, the first thing that the cyclist would do is, do they take steroids or not? So let's go through and have steroids, not steroids. And we know that this one is 2%, 98%, right? Where'd those come from? They gave them to us. They're right here in the second sentence. All right, now you took steroids. The test comes back positive for steroids. The test comes back negative for steroids. All right, you didn't take steroids. The test comes back positive. You can still have the test come back positive even if you didn't take them. It's not fair, but that's the way tests work. Or the test comes back negative. And these numbers are all given in the problem. You just have to read it carefully. All right, so you took steroids. What's the probability that the test will be positive? 99%. So we've got 99%. If you took steroids, the test is going to catch you 99% of the time. What does that mean about when it's going to come back negative? It means 1%. All right, and then if the cyclist did not take steroids, what's the probability it comes back positive? Well, we've already talked about that. It's 3%. If you didn't take steroids, what's the probability that it comes back negative? 97%. And then what you can do is you can multiply through these chains to figure out what's the probability of each event. So you can go through and do 0.02 times 0.01, for example, to figure out you did steroids, but the test comes back negative. The probability of that is that's going to be 0.002 or 0.02%. Okay, hold on. I think I went through and calculated all these just to speed this up. Where is it? There it is. All right, so what's the probability that you took steroids and the test comes back positive? That one's going to be 1.98%. What's the probability that you didn't take steroids and the test comes back positive? That's about 2.9%. And what's the probability that you did not take steroids and the test comes back negative? That's about 95.06%. So you can go through and you can check each of those if you'd like. I did do some rounding, I think, on one of them. So one of them maybe is not strictly accurate, but they're all pretty close. So you can do like a probability tree like this with these dependent probabilities, where you have the first event, and then assuming that event happens, then what's the probability of the second event based upon that first event having happened. And so that's just maybe makes these problems easier to go through and do the sequence of events, given that you have dependence. All right, and then there's one more example. So one downside of doing these videos the way that I do them, I have no idea how long this is going to be. It's going to be like 3 hours long. People are not going to watch it. All right, so let's say we've got airport screeners. And they're checking for water. All right, so let's say 5%, suppose 5% pack a bottle of water. They forget that they're not supposed to. And then suppose 95% of the time, the airport security catches it. What is the probability a randomly selected person packed a bottle of water and was caught? All right, so we've got the probability. And so the order that we're doing it in is A is the second. So that's caught and packed a bottle of water. So that's going to equal the probability that they packed water times the probability that they were caught, given that they packed water. All right, and then what's the probability that they packed water? 5% of the passengers packed water, that's 0.05. And then what's the probability that you get caught? 95% of the time you get caught. So you get 0.05 times 0.95. We can break out our calculator. 0.05 times 0.95 is 0.0475. So that's 4.75%. And real quick, we'll do the tree. All right, so you've got, here we've got a passenger. So they packed water. And they did not. All right, and what are the percentages here? 5% pack water, which means that the complement of that does not, 95%. All right, and then if you packed water, there's a chance that you're going to get caught. You got caught. And we'll say not caught. And caught, 95%. 5%. Right, if you did not pack water, then you cannot get caught, right? So you definitely do not get caught if you did not pack water at all. So our tree is really going to have only 3 possibilities. So you could multiply So, 5% times 95% to figure out this one. We've already done that calculation, right? What did we end up getting for that one? Wait, that doesn't look right. Hold on. What happened there? Oh, no, that is right. That is right. 4.75%. It didn't look right. 4.75%. All right, and then we got 5% and 5%. So we can go ahead and break out our calculator for this. Is why you do a calculator, because even the math teacher gets confused. So you get 0.0025, right, which equals 0.25%, and then the rest is this one, 95%. 95% of the time you just don't do the water. So, oh, and then one thing I didn't mention about the tree is that if you go through and add up the ends of the tree, you always get 100%. So you add up to 100%. So they represent all the possibilities. 4.75 plus 0.225 plus 95 gets you 100. The same thing is true for the cyclists. Okay, that is finally the end of this video, and hopefully it's not 2 hours long. All right, so thank you for watching and making it to the end. See you next time.